Hello, and welcome to the CSE 100 discussion for PA6. For PA6, you'll be doing a few things. Namely, you'll be working out a couple practice problems involving the Aho-Corasick Automaton, the Burrows Wheeler transform, and suffix arrays. And we've linked the relevant course materials here, the hyperlinks, and you can find these slides in the description of the video, and then that way you can pull up the slides and click on these links. In addition to these practice problems, you'll also be implementing a couple algorithms. So namely, you'll be implementing the Burrows Wheeler transform algorithm that generates the Burrows Wheeler transform of an input string. And then you'll be implementing the algorithm that generates the suffix array of a given input string. Lastly, we just want to point out that for implementing your code, we highly recommend checking out the sort function for C++, and it's located at this webpage, and it even has a useful example that demonstrates how you can create your own custom comparator. And what that means is you can define a function to do comparison in your own custom way. And if you do want to use standard sort function, which we recommend that you do, you'll find it useful. Just make sure to include the algorithm library at the top. In this video, I'll be going through all of the items that you see listed here in this table of contents. So this table of contents is from the discussion slides, and again, the discussion slides are linked in the description, and of course they're also available just straight from the course discussion folder. And so if you do open the slides, all of these links are clickable, and they will allow you to jump down to a relevant slide if you're looking for something specific, because there's quite a number of slides. So yeah, when you open the slides, you can just click on whatever you need, but I'm going to be going through all of these in the same order that you see here. Let's go through a step-by-step example of how to go about building an Aho-Corasick automaton. So here are the general steps. First, we want to build a multi-way trie that contain our words. And remember that with a multi-way trie for any given node, it represents a prefix string of that trie. So the same, we want to think of nodes in the same way for our automaton. Then we want to add failure links to our automaton, and then lastly, we want to add dictionary links to our automaton. So first off, what are failure links? For each node in our automaton, remember a node represents a string from the root. So for each node in the automaton, we will draw a failure link from that node to the node that represents the longest suffix that exists in the automaton. So this means that every single node in our automaton will get one outgoing failure link. And this even includes the root node. And the root node is a special case. It gets a failure link from itself back to itself. And it's also important to note that the root node represents the empty string. So at a high level, what failure links represent, or what they do, is they map a string in our automaton to its longest suffix in the automaton. So let's see what this looks like visually. If I want to construct an Aho-Corasick automaton using the words that are listed up here in the top right, then the first step I need to take is construct a multi-way trie with these words, which I've already done in this slide. Next, what we'll want to do is create failure links for each one of these nodes that go from the node to the longest suffix in the automaton that exists, but that is not equal to itself. So in stepping through each of these nodes to figure out what their failure link is, I'm going to use different colors to mean different things. For example, I'm going to use green to indicate the node that we're currently on, and the string representation of that node will be indicated in the top right. So right now we're at the root node, and the root node represents the empty string. I'm going to use red nodes to indicate word nodes, white nodes to indicate non-word nodes, and dashed blue lines to indicate failure links that we add. So let's take a look at the root node. The root node is a special case. As I said, it represents the empty string, and all we do is add a failure link from itself to itself. So we're done with that. Next, let's assess this node. So this node represents the string A, and we're going to consider all of its suffixes except for itself, and we're going to draw a failure link from this node to the longest suffix that exists in the automaton. So if we look over here, it turns out that the only suffixes that there are to consider for the string A is the empty string, right? Because we don't consider A, so the empty string is the only thing left. So that means that our failure link goes from the node back to the root, because the root represents the empty string. Okay, now let's assess this node. This node's string representation is AA. So the suffixes that we're going to consider looking for in order from longest to shortest is A, and then the empty string. So first we can see, does A exist in our automaton? So we start at the root node, and yep, A does exist in our automaton. So we've found the longest suffix that exists, and we draw a failure link from that node to that longest suffix. Now let's assess this node, and it represents the string AAT. So we're going to consider, again, all of the suffixes except for itself in order from the longest suffix to the shortest suffix. So the first one we'll consider is AT, and if we don't find that, we'll look for T, and if we don't find that, we'll draw a failure link to the root node. So first let's look for AT. So we start at the root node, and if we're looking for AT, we first ask, does this have a child that is A? And it does, so we follow it, and now we're here. Now we want to know if this node has a child T, and it does. So we get to here, and we've successfully found that AT is a string in our automaton, so we've found the longest suffix of AAT that exists in the automaton, and we draw a failure link going from it to here. Now let's assess this node, which represents AT. The suffixes that we'll consider are T and the empty string. So first we'll look to see if T is a suffix. So we start at the root node, and we ask, is T a child? And it's not. So we know that T does not exist in our automaton. Next is the empty string, so that means that we will draw a failure link from this node to the root. Now let's consider this node, which represents the string ATC. So we're going to consider the suffixes TC, and then C, and then the empty string. So we'll start with TC. Let's check if TC exists in our automaton starting at the root node. So is T a child of the root node? No, it's not. So therefore we know that TC is not in our automaton. So TC is a no-go. Next we check C. Okay, we start back at the root. Is C a child? Yes, it is. So we've found it right here. So we've found that the longest suffix of ATC that exists in our automaton is C, and so we draw a failure link from this node to C. Next, let's assess this node. This node represents the string ATCG. So we have quite a few to check here, but the first one that we check for is TCG, then CG, then G, and then the empty string. So we go back to the root node. If we're checking for TCG first, we ask, does this have a child T? And no, it doesn't. So we already know that TCG is not a string in our automaton. So TCG is out. Let's check for CG. Okay, so we start at the root node. Is C a child? And it is. Okay, so we found C. Now we want to know, is G a child? And it is. And so we've hit this node, and so we've found that CG is the longest suffix of ATCG that exists. So we draw a failure link from it to CG. Next, let's assess C, and the longest and only suffix that exists in the multi-way trie is the empty string, and so we draw a failure link from it to the root node. Next, let's assess CG. So we're going to consider the suffixes G and the empty string. So first let's check for G. Start at the root node, and we ask if G is a child, and it is. And so that means that we've found the longest suffix of CG that exists in the automaton. And so draw a link from it to its longest suffix, which is G. Next, let's look at CGC, right? So this node represents CGC. We're going to consider GC, and then C, and then the empty string. So first, let's start with GC. So we start at the root node. Is G a child of the root? Yep. So we follow it. Now we're here, and we ask, is C a child of this node? And yes, it is. So we've found this node, which represents the longest suffix of CGC. So we draw a failure link from it to GC. Next, let's look at this node, and you'll notice a pattern, right? So all of these nodes that are one away from the root, they're going to have a failure link to the root, right? Because for any strings that are just one character long, since we can't consider the whole string itself, the only option is the empty string. So for all of these that are just like one degree away, we know that the failure link will go back to the root. So the same is the case for G here. Okay, so now let's consider GC. So GC, we're going to consider the suffix C first, and then if not, we're going to draw a failure link from GC to the root. So let's go to the root node. And we asked, does it have a child C? And it does. So we found the longest suffix of GC that exists in our automaton, and we draw a link from GC to C. Next, let's look at GCA, right? So we're here. GCA, the longest suffix is CA, then the next longest is A, and then, of course, the empty string. So first, let's look for CA. So let's start at the root node. If we're looking for CA, we first ask if it has a child C, and it does, so we follow it. Now we ask if this one has a child A, and it doesn't. So that means we know that CA is not in our automaton. So we move on to the next suffix to look for, which is A. So let's go back to the root node and ask if A is a child, and it is. So we follow that edge, and we've found the longest suffix of GCA that exists in this automaton. So we draw a link from GCA all the way over to A. Okay, so next let's look at GG. So the suffixes that we're going to consider are G and the empty string. So first we consider G. Let's go to the root and we ask, does it have the child G? And it does, so we follow it, and we found the longest suffix of GG in our automaton. So we draw a failure link from GG to G. Okay. Next, let's look at this node, which represents GGG. So the suffixes that we're going to consider are first GG, and then G, and then the empty string. So first, let's look for GG. So we start at the root node, and we ask if it has a child G. It does. We follow the edge, and now we're here. Cool. Now we ask, does this have a child G? And it does. We follow it, and cool. So we found the longest suffix of GGG that exists in the automaton, which is GG. So we draw a link from GGG to GG. Okay, next, we're going to check the string GT. So we're going to consider the suffixes G and then the empty string. So first, let's see if T exists in our automatons. We start at the root, and as we've seen in many cases before, we know that T is not a child, so we know that T is out. So now let's check, or we don't have to check the empty string because T is not a suffix. That means that we're going to draw a failure link from GT to the root node. Okay, and the last one, we're going to look at this node, which represents GTA. We're going to first consider TA, and then we'll consider A, and then we'll consider the root in the last case. So first, let's see if TA exists in our automaton. So we start at the root node, and we ask if T is a child, and T is not a child. So we know that TA is not in our automaton. Now, next, let's look to see if A is in our automaton. So we start at the root, and A is a child. So we've found the longest suffix of GTA, which is A. And we draw a really long failure link from GTA all the way over to A. Cool, so now we have added all of our failure links for each node. So we just went through and added failure links for all of the nodes in our automaton. But I just want to take a moment to pause and mention something that's pretty cool. And that's that we can use dynamic programming to generate failure links. And if you are unfamiliar with what dynamic programming is, essentially what it means is we've divided our overall problem, which is generating failure links for all of the nodes in the automaton. So we have divided up our overall problem into smaller subproblems, where the results of earlier subproblems help us compute the results for later subproblems, usually by making that computation faster. So in this case, what it means is by solving for what the failure links are for previous nodes, it helps us to quicker compute what the failure links are for later nodes using those results that we already have. So if you want to do this, if you want to do dynamic programming to generate failure links, what you do is you do a pre-order traversal of the automaton. And so we know that there's a special case for the root, that we create a failure link from the root to itself. Besides that, how it works is what we're going to do is let P denote the parent of some node U that we're currently at, and let F denote the target of the failure link from P. So U is our current node, P is the parent of our current node, and F is where the failure link that's going out from P, which node it's incident on. So if F has a child labeled by the same letter as the multi-way try-edge going into U, then we create a failure link from U to that child of F. Otherwise, if not, and if F is also not the root, then we recurse by assigning F to be the target of the failure link from F. And then otherwise, we create a failure link from U to the root. So that's just a walkthrough of the algorithm. But let's see a couple examples, because we can look at the failure links that we just generated in the previous example, and we can show that we can apply this algorithm and we'll get the same results. We'll get the same failure links that we found from before. So let's look at a couple of the failure links that we generated from before, but let's instead generate them using this algorithm. Okay, so I've rolled back quite a number of steps back to the point that we were at when we were still generating, we were in the middle of generating failure links for our automaton, and the current node that we were at was this node, which represents the string ATCG. And we found the failure link by considering all the suffixes from the longest one to the shortest one, and then drawing a failure link to the longest suffix that we find. What we can do is let's try applying that algorithm, that dynamic programming algorithm that we just described. So what that algorithm says is, given some node U, so U here is our current node, and its parent, so this is its parent, and F, which is the target of the failure link that's coming out from the parent. So if we follow the failure link going out from the parent, this is the target, so this is F. So what we do is we check F's children, and we ask, do any of the edges, do any of F's children, the letter along those edges, is that a match for the letter that's along the edge from the parent to our current node U? So in this specific case, what we're asking is, does this node contain G as a child, since this edge represents G? And so since it does, that means that we've found where the failure link from this node is going to end up. So we can click forward to confirm that's what we got, and it is. So we draw a failure link from this node to that node using the logic from the dynamic programming algorithm. Okay, let's try the same thing, but for one more example that's a little trickier. So right now I've gone to the point where we were in the middle of generating failure links, and the current node that we were at was this node, which represents the string GCA. And so again, how we were doing it was we were considering the suffixes and then drawing a link from this node to the longest suffix that existed in our automaton. But instead, let's try applying that dynamic programming algorithm. So again, our current node U, that's this node. And then we have the parent, which is this node. And then F, which is the target, is where the failure link going out from the parent ends up. So we have the parent, we have its failure link, and we follow it. That means that this is the target. This is F in the algorithm. So we ask the same question as in the last example, which is, does F have a child whose edge matches the edge from the parent to our current node U? So in other words, since the edge from our parent to our current node is A, we're asking if this node F has a child A, and it doesn't have a child A. So we know that the failure link that is outgoing from this node does not go to a child of C. So now what's next? So since we don't have that case, we check the next case, which is if F is not the root node, then we're going to recurse by updating F to be the target of the current F. So the current F is this node, and its failure link target is the node that when we follow the failure link, it's what node we run into. So we take F, we follow its failure link, and its target is the root node. So that means now we're going to consider our new F to be the root node, and we're going to ask the same question, which is, so we're looking for F to have a child A. That's what we want to look for to see if we have a failure link. So we're at our new F, and we look at its children, and it does have a child A. And so that means that this node is going to be where the failure link that is outcoming from this node ends up. So we can click forward and make sure that this is what we got the first time, and it is. So that's pretty cool. You can also use this dynamic programming approach in your implementation. And this kind of worked out because in going through this example the first time, we happened to do a pre-order traversal. So that's why this is working, because the algorithm calls for a pre-order traversal. It depends on that. Now that we've added our failure links, the next step that we want to do is add any dictionary links that we might have. So even though each node has one outgoing failure link, it's not the case here that every node gets a dictionary link. So how we can determine where we have dictionary links is by traversing failure links. So what we do is for each node in our automaton, we traverse the failure links back to the root node. We follow them. And if along our traversal, we hit a word node, the very first word node that we hit, we will draw a dictionary link from the node to that word node. If you don't find any word nodes in your traversal, it just means that we don't add a dictionary link. So at a high level, what this means is that we're mapping a string to its longest suffix in the automaton that is also a word node, and also, of course, not equal to itself. So let's see what this looks like visually, because I think it's a little bit easier to understand that way. Okay, so now that we have found all of our failure links, let's now add dictionary links to our automaton, if there exist any. So I'm going to use a similar color scheme in this example. So red nodes still mean word nodes, white nodes still mean non-word nodes. Failure links will be indicated in blue. Dictionary links will be indicated in orange, so that's new. but then the current node that we're assessing to see if there is an outgoing dictionary link, that will be indicated in green again, and the string that represents that node will be indicated in green in the top right, just like before. And if you'll notice, the gray links that you see here, these are the exact failure links that we found in the last part of the exercise. And the only reason that I've made them gray is because in going forward, we're going to traverse the automaton and assess each node. And when we start drawing dictionary links and looking at paths of failure links, it might get a little bit confusing. And so I've just grayed them out, because what we'll do for each node is we are really only going to consider the path that goes from that node back to the root along failure links. So for each node, we traverse back to the root along failure links. So that's the only path that we care about when determining whether or not to add an outgoing dictionary link from that node. And so whatever that relevant path is, I will highlight in blue, so we know like what to pay attention to and what we care about for that node. Okay, so let's start at this node, which represents the string A. So as you can see, I've highlighted the path back to the root along failure links. So in this case, it's just one failure link, and then we get back to the root node. But what we do is along our traversal back to the root node along failure links, if we hit a word node, then the first word node that we hit, we will add a dictionary link from that node to the word node. And if we don't hit a word node and we make it all the way back to the root, then that just means that we don't have a dictionary link outgoing from the current node that we're at, the green node. So what we can do is traverse the failure links, in this case just one, back to the root and see if we hit a word node, and we don't, right? We go straight to the root and we didn't hit any word nodes. So that means that this node does not have any outgoing, does not have an outgoing dictionary link. Okay, now let's take a look at this one. So you can see that its path back to the root is highlighted in blue, so along the failure link. So we're going to do the same thing. We're going to traverse the failure links back to the root, and if along the way we run into a word node, then the first word node that we encounter, we will add a dictionary link to it. So let's traverse. So we're here, we traverse, get to this node, and this node is not a word node, so let's keep going. We traverse and we hit the root node, and we didn't find any word nodes along the way, and so there's no outgoing dictionary link from this node. Okay, now let's consider this node. Okay, we're going to do the same thing. Let's traverse the failure links back to the root and see if we hit a word node. Okay, this is not a word node. Let's keep going. And we get back to the root, and we didn't find any word nodes. So there's no outgoing dictionary link for this node for AAT. Now let's try this one. Same thing. Let's traverse the failure link back to the root, and we didn't hit a word node, and so same result. We do not have a dictionary link that is outgoing from that node. Let's try this one. So same thing, let's traverse the failure links back to the root and see if we hit a word node. So we traverse and we encounter this node, and this is a word node. So since we've hit a word node and it's the first word node that we hit, we're going to stop and we're going to add a dictionary link from that current node to the word node that we encountered on our traversal back to the root. Now let's consider this node. Let's do the same thing. Let's traverse the failure links back to the root. We go here. This is not a word node, so let's keep going. And this is a word node. So we did encounter a word node on our traversal back. And this is the first word node that we encountered on our traversal back. So we add this big swooping dictionary link from our current node to this word node that we encountered. Now for this node, we traverse our failure link back to the root. We didn't hit anything. Cool, so there's no dictionary link that is outgoing from that node. Okay, let's look at this one. let's follow the failure links. So we follow this one, and we do encounter a word node. So we have a dictionary link to add from this node to the word node that we encountered. Okay, now let's do this one. Let's traverse failure links back to the root. So we go here. That's not a word node, so let's keep going. And here we do encounter a word node. So that means that we're going to add a dictionary link between our current node and the word node that we encountered. So we added it right there. Okay, now for this node, the failure link just goes straight back to the root. So we definitely don't have a dictionary link outgoing from this node. Okay, now we're here. Let's traverse. So we go along this failure link and we encounter a word node. So we add a dictionary link from our current node to the word node that we encountered. Okay, now we're at this node. So let's traverse the failure links all the way over here, and we get to this node. That's not a word node, so let's keep going. And then we hit the root. And in our traversal, we didn't hit a word node. So that means that there is not an outgoing dictionary link from this node. Now let's look at this node. So let's traverse the failure links. We go along this one, and we hit a word node right here. So that means that this one will have an outgoing dictionary link from itself to that word node that we encountered. Now for this node, same thing. Let's traverse the failure links. So we traverse failure link, and oh, we already found a word node right here. So we add a dictionary link from this node to the word node that we encountered. Also note, it's important to note that you can see that if we, continued following the failure links, that we would encounter this other word node. However, the algorithm doesn't work that way for adding dictionary links. Once we, when we find the first time that we find a word node, we add a dictionary link and stop when we're done for that node. So we don't like keep going and then add another dictionary link. Okay, what about for this node? So let's traverse the failure link back to the root, and we didn't encounter a word node, so there is not an outgoing dictionary link for that node. Now let's look at this node. So let's traverse its failure link. Okay, now we're at this node. Let's traverse its failure link, and we're back at the root, and we didn't hit a word node, so that means that this node does not have a dictionary link coming out of it. Okay, so great. Now we have fully constructed our automaton. We've added all of the failure links and the dictionary links that exist in it. Okay, let's say that now we have a multi-way try that is much, much larger, and we want to construct an automaton for it. But specifically, what we want to know is where the dictionary links are going to exist. This is very similar to a part of question 1 in the PA. So if we want to find the dictionary links, how we did it before is we first constructed all of the failure links, right? And then after constructing the failure links, we went through each node again, and we did a traversal back through the failure links to see if we hit a word node. For something as big as this, if we're doing this on paper, that seems like it might get kind of hairy. There's going to be lots of lines being drawn everywhere, right? So is there a way that we can kind of logic our way through this without drawing all of the failure links? So there are a couple things that we know. One thing we know is that we only get dictionary links if for some string in our automaton, there exists a non-prefix substring of it that is a word in our automaton. More specifically, a dictionary link will be drawn from a node to its longest suffix that is a word in the automaton, and that is also not equal to itself. So think about that for a second. Pause the video if you need to. So let's go through each of these words. We're going to scan them to look for dictionary links that would exist in such a constructed automaton. And essentially what we will need to do is, for each word, we're going to see if a substring in the word is another word that exists. So let's go through examples. Okay, so let's say we're starting with the word ang. What we're going to do is we're going to consider the whole word except for the first letter. So we're just going to consider the last three letters of ang. So what we do is we look at ang and we ask, does this contain a substring that is also a word in our automaton? And the answer is no. And since it's no, that means we're not going to have any outgoing dictionary links from the nodes within the string ang. So that means for this path right here, for the nodes in this path, we're not going to have any outgoing dictionary links in a constructed automaton. Now let's scan this string. Again, we're not going to consider the first character. So really what we're considering is vatar. So we ask, does vatar contain a substring that is a word in our automaton? And this does not contain a substring that is a word, one of these words. And so since it doesn't, that means that we know that for the nodes along this path right here, avatar right here. So any of these nodes, these nodes do not have outgoing dictionary links because there is no substring in vatar that is also a word in here. Okay, now let's consider the next word, which is avatar ang. So we're going to scan avatar ang for substrings that are also words in our automaton. But really, like we said, we're not going to consider the first character. So really what we're scanning is vatar ang to see if it contains any substrings that are words in our automaton. So is this the case for vatar ang? And it is. When we scan this, we find the word ang, A-A-N-G. That's one of our words. It's the first one up here. And because we found this, we know that there's going to be a dictionary link that is outgoing from the node representing the string avatar ang, which is right here. And it's going to be incident on the string representing ang, which is right here, right? So that's how, that's why we connect a dictionary link from avatar ang to ang. However, how do we know this? Like just based on the fact alone that, you know, we found a substring that's also a word in our automaton. How do we know that it's outgoing from here and incoming into here? And one way that you can think about it is thinking back to the way that we have been adding dictionary links before, which is for some node, you know, assuming that we've already constructed the failure links. And what we would normally do is traverse back through those failure links until we hit a word node. And if we did, we'd make a dictionary link, or otherwise, you know, we'd run into the root node and then not add anything. So we can imagine like, so we're considering avatar ang, right? So it's kind of like if we were doing our normal steps, right? And we were going through all of these nodes, and then right now we're currently at this node, right? For the string avatar ang, we're currently at this node, and it's as if we were wondering, you know, okay, now let's add a dictionary link, and you know, think about how you would normally go about that, which is we would normally follow the failure links back until it hit a word node, right? So it's useful to think about what the failure links represent. So we don't have failure links explicitly written out here. However, we know that the failure link that is outgoing from this node will point to the longest suffix in the automaton. So the longest suffix of avatar ang that's not itself, that exists in the automaton, that's where this one's failure link will go to. And then wherever that is, that one's failure link will go to its longest suffix. And then that one's will go to its longest suffix and so forth, right? And so what this means is that if a dictionary link, if an outgoing dictionary link from this node exists, where it will point to is the longest suffix of vatar ang that is also a word node. So that's the property, that's like the statement that we made a few slides ago, but that's the reasoning for it. That's why we can make this we can logic our way through this in this way. So again, that was if a dictionary link, if an outgoing dictionary link exists at this node, then where it will point to is the longest suffix of that string that is not itself, but that is a word in our automaton. So let's look back at our string again. So since we're not considering itself, we are looking at vatar ang. Let's see what all of the suffixes are of this string. So we have vatar ang, that's not a word in our automaton. We can look at atar ang, that's not a word. Thar ang, nope. R ang, rang, nope, none of those are. Now when we consider the capital A-A-N-G, we do find a suffix that is a word in our automaton. So we have found the longest suffix of avatar ang that is not itself, but that is a word in our automaton. So we know that we will be drawing a dictionary link from that node to the node representing that longest suffix that is also a word. Okay, now let's try Firelord. So we're going to scan the string Firelord, but we're going to omit the F, so really, I guess, Irelord. And so we asked, does Irelord contain a substring that is a word in our automaton? And it does not. And so we know that among these nodes for Firelord, which are here, none of these nodes are going to have outgoing dictionary links. Next, let's look at Firelord Ozai. And so what we're really looking at is Irelord Ozai. And so we ask, does Irelord Ozai contain a substring that is a word in our automaton? And it does not, right? There's no substring in here that is one of these words. And so we know that none of these nodes here are going to have any outgoing, or well, you can only have a maximum one, but none of these nodes will have an outgoing dictionary link. Now let's check the string the avatar. So we're really going to be checking out the string, I guess, he avatar. And so we asked, does he avatar contain any substrings that are also words in our automaton? And yes, it does contain a substring that is a word in our automaton, and that substring is avatar, right? So here's that word. And so for the same rationale as for the previous case of avatar ang, we know that there's going to be a dictionary link that goes out from the avatar to avatar. And we can confirm that our reasoning from the previous example with avatar ang, for the reasoning that we drew this, we can apply the same logic here, right? So if we're considering he avatar, if it does have a dictionary link, then the dictionary link that it will have is, it will point to the longest suffix that is a word node in our automaton that is not itself. So the longest suffix that is a word node is avatar. So that's consistent, right? So it has a dictionary link going to avatar. Okay, let's do one that's a little bit more tricky. So the current word that we're going to scan is the avatar and the Firelord. So again, in reality, we're just checking, we're checking the whole string except for excluding the first character. So really what we're scanning is he avatar and the Firelord for substrings that are also words in our automaton. So maybe give it a few seconds, give it a minute, however much time you need. Think about what substrings we're going to find that are also words. And based on that, think about how you think it's going to change the automaton. So if you'd like, you can pause the video. Otherwise, I'm just going to resume in a few seconds. So what ends up happening is when we scan he avatar and the Firelord, we find 3 substrings, not just one, that are words in our automaton. So we find avatar, we find the Firelord, and we find Firelord. And in case you missed what happened, how this result affected our automaton is that we added a dictionary link from here to here. So we added a dictionary link connecting the avatar and the Fire Lord to the Fire Lord. Now, why is this the case? We found 3 substrings, yet we only added 1 dictionary link. So let's see why. Let's consider each of these separately. So recall again, so we avatar, the Fire Lord, those are the 3 substrings that we found that were words. So let's take a look at each of these separately. So we'll take a look at avatar first. So we were scanning he, avatar, and the Fire Lord, right? So that's this path right here. So he, avatar, and the Fire Lord. Specifically, this substring avatar, in this string, like where that's at in the automaton is right here. Like we're talking about this spot right here, right? So meaning the string that ends right here. So what that means is that we're going to have an outgoing dictionary link from this node to the longest suffix of this string that is also a word node, or that is also a word in our automaton. However, we already did this, right? We just basically found the same dictionary link again, right? So for he avatar, you can kind of think of like split the string right here. Like we're only concerning ourselves with he avatar right now. Like if we were traversing, right? And we were at this spot, then we can reason that if an outgoing dictionary link exists at this node, then where it will point to is to the suffix, the longest suffix that is also a word node. And the longest suffix of he avatar that is also a word node is avatar. So we would draw a dictionary link to there, but we already found that one. So that's one reason why we didn't see like more than one dictionary link, right? So we found a repeat. Okay, so moving on. So what about the fact that we found both Fire Lord and the Fire Lord? Like, what does that mean? Why did we only draw one dictionary link? So we can apply the exact same logic that we've been applying the whole time, right? So we're considering the string he, avatar, and the Fire Lord, right? So it's right here. So really, it would be like as if we were traversing, right? Like if we were traversing, checking each of these nodes and following their failure links and seeing if we ran into word nodes, blah, blah, blah. We did it for all of these. And then we got to this one. And we also, we did the same thing and traversed the failure links. However, instead, what we can ask instead, since we don't have explicit failure links written out, is we can use the same reasoning, which is if an outgoing dictionary link exists at this node, where it will point to is the longest suffix of this string that is not itself, that is also a word in our automaton. So in other words, he, avatar, and the Fire Lord, of the green substring, right? We exclude the T, from he, avatar, and the Fire Lord, what is the longest suffix of this string that is also a word node? And that is the Fire Lord. Even though Fire Lord is also a word, the dictionary link will be drawn to the longest suffix that's a word. So that's why a dictionary link gets drawn to the Fire Lord instead of being drawn to Fire Lord, or instead of being drawn to both. So that is why, even though we found 3 substrings, we only added 1 dictionary link from scanning the avatar and the Fire Lord. Okay, the last one. So the last one is we're going to scan the word the Fire Lord. And so what that really means is we're scanning he, Fire Lord, to see if it contains a substring that is also a word in our automaton. And is that the case? Yes, it is. We have the substring Fire Lord that is a word in our automaton. And so that means that we are going to be drawing a link from the Fire Lord to Fire Lord. And so now, using the logic that we did alone without explicitly constructing any failure links, we've been able to figure out where all of the dictionaries in such an automaton where all the dictionary links in such an automaton would exist if we were to fully construct it. Okay, so let's review how to construct suffix arrays. Given some string s, first what we do is we list all of the suffixes of s, including the full string. Next, what we do is we order these from least to greatest, noting the index that each of the suffixes start at in the original string. And then lastly, using this order, we assign the elements of the suffix array to be those starting indices of each of those suffixes. So let's take a look at an example. So let's say that our input string is doggo. So we see in the table at the top row is the index of the character, and the bottom row is the character at that index. So this is just the original string. So first what we do is we list out all of the suffixes of doggo, including the full string. So you can see here's the full string, and then here's, right, and it starts at index 0, and then the suffix that starts at index 1 is ago, the suffix that starts at index 2 is the ggo, the suffix at index 3 is go, and the suffix at index 4 is o, and we don't include the empty string. So now we've listed all of the suffixes of doggo and the index that they start at in the original string. So next what we want to do is order these alphabetically. So when we do this, this is the result that we get. So notice that, so for example, so doggo is less than ggo, right? Because D is less than G. Ggo is less than go, because even though, so the G is the same, but the second character, G, is less than O. And then between these two, G is less than O, and so go comes before O. And then in comparing these last two, O is less than ago because O doesn't have any character after it, so we consider that less than G. So now we've ordered our suffixes alphabetically, and we still have what their starting index is designated on the left. So now all we do is we grab these starting indices, starting from the top going down. And so 0, 2, 3, 4, 1, 0, 2, 3, 4, 1. So this would be our resulting suffix array. Okay, so when it comes to implementing the algorithm that will generate the suffix array of a given input string, what's probably most natural and straightforward to think about doing is first generating all of the suffix strings and then putting them into a vector before proceeding to sorting them and doing the rest of the algorithm. However, when might this be a problem, or rather, why might this not be optimal? So give yourself maybe a minute to think about it, and you can pause the video if you'd like. And so the issue here is that if we have an input string of length n, and we're storing all of its suffixes, that means that we're using up O of n squared space, which is something that can quickly blow up, especially if we're working with very long strings. So the question is, can we do better than this? And if so, how can we do better? And the question obviously hints at the fact that we can do better, but maybe give yourself a minute to think about how you would improve upon this. And pause the video if you would like to. And so it turns out that we actually can do all of the suffix comparisons using constant space. We can do this by simply scanning the string and comparing pairs of indices at a time. So let's see what this looks like with pseudocode. So given some string s as the input, we can first create an array containing the integers 0 through the size of the string -1. Then we can create a custom comparator. And what it means to create a custom comparator is to create a function that does your own custom comparison that you define. So you can create a custom comparator where for two integers I and j, it will return that I is less than j if and only if the substring that starts at index I is less than the character at index j. And what you want to do is sort your array using this custom comparator. And earlier, when we mentioned resources and links for the PA, there was a link to like a CPP reference link to the sort function. And if you click on that link, you'll see there's an example of someone who defined their own custom comparator, and you can see how it's done and how it's passed in. And so you can think about implementing your own custom comparator and calling it the same way in that example. But the point is that we're simply scanning through the string, and we're just comparing 2 indices at a time. We're not allocating any extra memory other than whatever we're using just for those 2 indices at a time. So in this way, we are only using constant memory to do this. Okay, so let's review how to compute the Burrows-Wheeler transform of a given string. So given some string s, and we're going to consider the input string to have a terminating character appended to the end of it. So we have s with like a $sign at the end of it in our case. So given this input string, we generate all of the rotations of this string, and then we order them from least to greatest, just like we did with the suffix array in ordering the suffixes least to greatest. Once we order these rotations least to greatest, we want to graph what the last character is of each of the rotations. And when we look at those from top to bottom, we have our Burrows-Wheeler transform. So let's see what that means in an example. Let's say that my input string is Google with a $sign at the end, and I want to generate its Burrows-Wheeler transform. So first what I do is I generate all of the rotations of this string. So we can start with the first one just being the string itself, the Google and then the $sign. And we're going to shift each character over to the right by 1 position. So the G will move over to the 2nd position, this O will move over to the 3rd position, and so forth. And then this $sign that's at the end, when it gets shifted to the right, it wraps around back to the beginning. So this is how we get this string from rotating this like once to the right. And then similarly, if we take this string and shift all the characters once to the right, we get this one and so forth. So in that way, we can generate all of the rotations of Google with the $sign. Next, what we want to do is take all of these rotations and order them alphabetically. So these have been ordered alphabetically in the same way with the same lexicographic comparisons that we used in generating the suffix array. And notice that the $sign Google is first. It's the least of all of these, and that's because, again, we consider the $sign, the terminating character, to be less than all of the other characters. So it goes first, and then the rest of these are sorted in increasing order. And then in the second column, we've noted what the last character is of each of these. So the last character of $sign Google is the E, last character of this string is the L, and so forth. And so now we have this column of characters. So lastly, all we do to determine what our Burrows-Wheeler transform is we take all of these characters in this column and put them into a string from the top to the bottom. So this is our Burrows-Wheeler transform of Google with the $sign. What if instead we want to go from a Burrows-Wheeler transform back to the original string that produced that Burrows-Wheeler transform? We can do that, and we'll do it graphically because I think it's a lot easier to follow when you see it visually than seeing written instructions. So the first step that we want to do is we take the Burrows-Wheeler transform, this string, and from left to right, let's insert it into this rightmost column from top to bottom. So the ELO $sign GOG, ELO $sign GOG. Next, what we'll want to do is alphabetize all of these characters and put them in the leftmost column. So when you alphabetize all of these, then you get this sequence. And remember, the $sign is less than all of the others. So this is what we get when we alphabetize it. The next step is we want to go down this right-hand column. And as we go down, we mark each character with a subscript indicating the nth time that we've seen that character. So let's see what that looks like. So for example, if I'm starting at the E, I give it a 1 because this is the first time I'm seeing an E. Now we go down to the next character. We have an L, and this is the first time I'm seeing an L, so I give it a subscript of 1. Then we go down, and this is the first time I'm seeing an O, so it also gets a subscript of 1. I see the $sign now, and this also gets a 1 because it's the first time I'm seeing this character. We go one more down, and I see a G, and this is also the first time I'm seeing this character, so this also gets a 1. We go down one more, and we see an O, but this is the second O that we've seen, right? We saw this one. And so since this is the second O that we've seen, we give it a subscript of 2. And then lastly, we hit a G, and we give it a subscript of 2 because this is the second G that we see as we're going down here, right? We saw this one first, and now we saw this one second. So this one gets a 2 as a subscript. And now what we want to do next is do the exact same thing, but for this column. So we can do the same thing. So this is the first $sign, so it gets a subscript of 1. This is the first E, gets a subscript of 1. First G gets a subscript of 1. This is the second G, so it gets a subscript of 2. The first L gets a subscript of 1. The first O gets a subscript of 1. And the second O gets a subscript of 2. And so now what we want to do is start reconstructing. And what we do is in the right-hand column, we start at the $sign, and we're going to look over to see what character is in the left-hand column at the same row. So again, $sign, we look over, we see that G2 is what is in the same row as it in the left-hand column. This means that G2 is what we're going to append onto the string that we're going to grow here in the first row. So starting with the $sign and then adding on G2. So again, we started with the $sign, we saw what character was in the same row as it, and then we added it to the first row. So we're appending it onto the $sign. And at the end of this algorithm, we'll have the original string reconstructed. Okay, so we just did G2, right? So now we go to where G2 is in the right-hand column, and we do the same thing. So we found G2, and we look over to see what character is in the left-hand column, and that's O2. And so same process. Now we're going to append O2 onto this growing string that we're making here. We add O2 here. And we repeat the same process. So we're at O2. So now we find where O2 is in the right-hand column. We found it. Now we find what is in the left-hand column in the same row as it, and it's O1. So that means we're going to add O1 here, which we do. Now we have O1, so let's look for it over in the right-hand column, and it's right here. So now we look to the left, and in the left-hand column, we see G1. So G1 is going to be what goes here. And now we have G1, so let's look for G1 in the right-hand column, which is right here. And now we traverse, or we don't traverse, but we look over to the left to see what character is in the left-hand column, and it's L1. So L1 is what's going to be added to this next spot. And now we've reconstructed our whole string, right? You see Google right here. The only thing is that we have $sign Google, whereas before, if you recall, our input string into the BWT algorithm was Google and then a $sign instead of $sign Google. So the last step that we need to do is simply take our result, except move the $sign to the end, essentially. So this would be our result, and we've recovered our original input to the Burrows-Wheeler transform.